Okay, so the slides are all visible, right?
Yes.
Okay, sure.
Yeah, you can go ahead.
Okay, all right. So sir, also live streaming, is it also on?
Yeah, that is on. Okay,
Okay.
you can actually do the recording yourself, I think.
Yeah, sure, I'll do that.
Or I can do it too. I'll do it. Yeah, I've done both. You
Okay,
can go ahead.
thanks. Okay, so yeah, so last time we were talking about the KSX system more, I guess, from a historical point of view and a point of view of where it sort of lies in the industry. So if you remember, there is this XSXU system that is based on a lookup table that is, being certified by the FAA for unmanned collision detection, right? So this is for unmanned collision detection, and this is for, completely human independent automatic collision detection advisories for unmanned vehicles. What we are going to look at is a compressed version of this that uses DNNs for compression. So we talked sort of more at a high level last time. So this time what we're going to do is we're going to go into some of the details of what the inputs to the DNNs are, what the inputs to the ACAS system is, what the output to the DNN from the DNN is, and how do we interpret the inputs and outputs. What is the, the architecture of the DNN, the number of layers, the size, everything. Okay. So let's look at all of that. Right. So let's talk about what the inputs are. So suppose you have this sort of a picture. The picture is, I guess, the size is okay. Can you read these variables?
Yes.
Probably, yeah, okay, sure. So suppose if you have this sort of a picture, then there are basically 7 variables that are being used here, or that the ECAS system uses here to describe this. Okay, so for the moment, forget about the fact that we're actually in 3D space, and let's say that the two aircrafts are in the same plane. Then we have sort of 5 variables that we'll need to worry about. The first one is, of course, what is the distance between these two aircraft, right? And that is the first variable, usually written as rho. This distance is, or okay, so all distances in the ECAS system are said to be given in feet, but units don't really matter when you, by the time you come to the DNN side of things, because things will always be normalized and so on. But in basically, this one of the inputs to the system is this distance between the two aircrafts in rho. So for example, if the system is using transponders to get its data from the sensors and so on, that layer will compute the distance to the intruded aircraft and it will pass it to your ECAS system. So that is one of the inputs. Input number 2 is basically what is the angle of the intruded aircraft at which it is at, right? So if you want to describe where relative to your position the intruded aircraft is, you have to sort of give it both a distance and a direction as some sort of an angle, right? So this second variable is the angle, and it is measured in anti-clockwise sense, and it's measured from the direction in which you're traveling, right? So for example, if this is your plane, then we know that you're traveling in this sort of a direction. So if the intruder is, say, somewhere, as in the picture, let's say if it's somewhere here, then what we're going to do is we're going to draw the line connecting your plane to the intruder, and we're going to measure the angle against the direction in which your plane is traveling in an anti-clockwise way. So we're going to measure essentially this angle. So this angle is called the angle to the intruder, and it's denoted by theta. So this is the second input, right? So similarly, if the intruder was on the other side and your plane was like this, let's say, then the angle would have looked like something like this. Okay, and this angle, it is measured sort of anti-clockwise, and it is actually given in a range in radians, and it's between minus pi and pi, right? So for example, in this particular situation, your angle would actually be something like minus some particular degree, right? Because it is more than 180 degrees. So what you would be basically measuring is this angle and taking the negative of it. Okay. Although the diagram which, this diagram is by the way from Guy Katz's Reluplex paper. This is Reluplex from Guy Katz and others. So I think their paper is the first one which came up with this really nice diagram of the ACAS-XU inputs. But yeah, one of the things to keep in mind is that if in this sort of situation which is there in the paper, the actual angle that ACAS-XU expects to get as input is basically this angle but taken negative. So if this was say something like, let's say it is pi by 6 or something like that, right? So then you would expect that, or ACAS-XU would expect that the angle as input would come as minus pi by 6, right? But if it was on the other side, if it was on the left side, then it would come as a positive angle. So one way to remember might be that you just measure it in the anti-clockwise direction from the direction in which you're traveling, and then you just you'd get an angle from 0 to 2 pi. You convert that to an angle from minus pi to pi, right? So these are the two inputs: the distance to the intruder and the angle of the intruder, right? And these two together gives you the exact relative position of the intruder to your aircraft. So far so good. The third is the direction in which the intruder itself is traveling. So it is this angle, right? And again, this is also measured anti-clockwise and measured with respect to the direction in which you're traveling. So if you're again in this picture, you're traveling directly towards the top of the page. So this is the sort of direction against which we measured the angle. And again, it's measured anti-clockwise, and again, it's angle between minus pi and pi. Right? So that is the third input. And the fifth input is, or sorry, the fourth input is
Diganta,
yeah.
I have a question.
Right.
So how do you define intruder? I mean, there are.
Yeah. So I'll maybe I should have made that clear, right? So one of the things about the ACAS-XU or even TCAS or any of these systems is these are designed to go on planes, right? So basically the idea is that in the real world, if two planes are approaching each other, let's call it planes A and B. So we have a situation where say A and B are both approaching each other. Then the way TCAS works and the way ACAS-XU is also designed to work whenever it gets deployed is that both of these planes will have their own sort of machinery or implementing the ACAS-XU system, right? So A has an ACAS-XU unit on it, and B also has an ACAS-XU unit on it, right? And the idea is that A's ACAS-XU unit will talk to B's and guide A to move in a way that will prevent a collision. And B's ACAS-XU unit will talk to A and guide B to move in a way that also prevents a collision. So basically, from each one of the ACAS-XU units perspective, the other plane is considered an intruder. And this particular ACAS-XU unit's job is to maneuver in a way that avoids that intruder. Does that make it okay? Clear?
Okay, so for each plane, the other anything other than itself is an intruder.
Yeah. And this happens. So all of these systems are usually considered with a situation where up to 2 planes will be colliding. None of these systems consider the case where maybe 3 planes might end up colliding. So that sort of a situation, yeah, these systems don't cover that. Even the legacy traffic collision avoidance systems, that also doesn't cover that. But yeah, all of these systems will basically just latch on to one particular plane considered as an intruder and then try to give you guidance as to how you can avoid that particular intruder.
Okay, got it.
Yeah. So, right. So I was talking about the third angle. The third angle is basically this particular angle, which is the direction in which the intruder is traveling. Now the fourth and fifth inputs are basically speeds respectively of your own plane and the intruder, and these speeds are relative to whatever frame of reference you're working with. So usually these are in terms of ground speeds, although that might not be, from a flying perspective, might not be very useful, but like usually when we think about these things, we think of in terms of ground speed. So this is ground speed. And okay, so assuming these to be ground speed is a simplification that sort of we are doing when we're analyzing these systems in real world. There might be things like wind. So it, it begs, or that there might be a discrepancy between airspeed and ground speed, and you'll have to consider all of those things if you want to do if you want to actually model the precise real life situation. But usually we just consider these as ground speed, and we consider that to be the same as airspeed. So that is what we consider, and these are again given in feet per second. So these two, and by speed, by the way, I don't mean vectors. These are just scalar speeds, the magnitude of the speed essentially, right? So these two are the speed of your own plane in feet per second and the speed of the intruder plane in feet per second. Okay. So these first 5 things essentially are giving you your speed, the intruder's information about the intruder's velocity, and the information about the intruder's relative position to you, right? So in 5 sort of inputs, we are covering all of those things, right? Because rho, so if you consider rho and theta, this will give you intruder's position respect to you. Similarly, psi and intruder speed gives you intruder's velocity. And of course, you have your own velocity, and your own velocity doesn't need to have associated direction because everything is actually with respect to the direction of your velocity itself, right? So yeah, so in terms of 5 inputs, we're giving all of this information, and this actually completely describes the 2-dimensional situation, at least relative to your position. So is this so far okay? Is the 2D inputs clear?
Well, to me, yes. Yeah.
Yeah. Okay. Sure. So now what happens, the question is what happens when you have an actual real life situation where some planes are not in the same plane, or they are not like essentially have the same altitude, right? So all of this is fine if they have the same altitude, if they're maneuvering in a plane parallel to the ground. But what happens if one of them is at some, say, 2,000 feet and the other one is at 1,000 feet, right? Because there is a vertical component to the way aircraft moves. So how do you describe the vertical component of the motion? So what they do, and this is actually somewhat standard in the sense that even the TCAS system uses this, they have this specific parameter called time to loss of vertical separation. So what they'll do is they'll take your aircraft, and let's say that it's climbing at certain rate, right? And then you have an intruder aircraft, and let's say that it's descending at certain rate. So you know that you are at this particular altitude and the intruder aircraft is at this particular altitude. And given your rate of climb and the intruder aircraft's rate of descent, at some point they will sort of come to the same altitude, right? They may not collide. It might happen that the intruder aircraft reaches the same altitude at this point, and the your own aircraft reaches the same altitude at this point, and the intruder aircraft reaches the same altitude at this point, right? So there's still some horizontal separation to them, but now they are at the same altitude. So whenever they are within some tolerance at the same altitude, we say that we have loss of vertical separation, right? And the way that we describe the vertical component of the situation is by giving an estimate as to how long it will take until there is loss of vertical separation, right? So for example, if your own aircraft is at 2,000 feet and the intruder aircraft is at 1,000 feet, and let's say that your own aircraft is descending at, say, 1,000 feet per minute, and the other aircraft is climbing at 1,000 feet per minute, then we know that in 30 seconds, both of them will be at 1,500 feet, right? So then 30 seconds is our time to loss of vertical separation. Okay. And this time to loss of vertical separation is the 6th parameter, tau. So is that clear? And notice that this actually, in some sense, it doesn't give you the complete information as to who's climbing and who's descending and so on. So, okay, one more thing I should probably have mentioned in the beginning, and there is two, as I mentioned previously, there was sort of two aspects of this ACASS system, right? There's a horizontal lookup table and a vertical lookup table. The vertical lookup table is almost emulates the TCAS system itself. The horizontal lookup table is what is more new and interesting. And all of these analysis of the DNN compression, and the safety verification of the DNN and all of that, they usually look at the horizontal component itself, which basically means that the system is only going to tell you to turn, not climb and descend. Okay. So yeah, so this is basically the sixth input, which is the time till the aircraft is the same altitude. So is that sort of clear? So notice that, this doesn't actually distinguish between situations of this sort of kind. So you can have, say, both of the aircrafts are, climbing from different altitude, let's say. So let's say that we have one aircraft which is the high altitude and climbing very slowly, and we have another aircraft which is the low altitude and climbing very fast. This might be one situation, and the other situation might be that, one aircraft is climbing and the other aircraft is descending. You might end up getting the same tau for both situations. But that is how they model their input space. They don't want to distinguish between those two situations when deciding where to turn to avoid. So remember that they are not going to ask the aircraft to change their vertical speed or their climb rate at all. They're just going to ask them to turn. So when asking the aircraft to turn, they don't really worry about who's climbing and who's descending precisely. They only worry about how far until they will actually come at a point where they have no vertical separation, right? So these are the first six inputs, and are the first six inputs clear? Are there any questions? So for example, in this particular picture, it might actually happen that, this is the top-down view, but this particular aircraft is actually, say.
So I have a question. So the sixth input tau is, I presume, is between one's own aircraft and the adversary.
Yeah. It is between one's own aircraft and the adversary. So tau is basically, it's measured in seconds. It's the time until which your aircraft and the adversary will be at the same altitude. So yeah, in that sense, it is sort of between one's own aircraft the same and the adversary.
So I presume the first five inputs, why are they required? I mean, along with that, I mean, if sixth the altitude is there, so it's still not clear to me from these six inputs if that covers all possible collision scenarios. Okay, so that is not clear to me yet. Okay, I mean, how many of the collisions it actually is able to handle of those cases and not. Okay, so I can see. So,
I'll draw a picture. Maybe hopefully that'll.
Yeah, but does it? Is it designed, the DNN said that it will handle all kinds of collisions between?
So the DNN is a question, but the input space is definitely modeled so that it will at least be able to model the possibility of all kinds of collision happen.
Okay. Yeah. How is still unclear to me, but I'll trust
I'll just
that you will explain later on, or
I'll just explain right now itself. So I'll try and explain right now. Okay. So I'll try to draw this sort of a 3D picture, if that is okay. Maybe that will basically help. So these two axes, these represent the ground, let's say. So this is sort of the ground level that we have, right? So now let's say that we have two aircraft. So our own aircraft, let's say, is blue, and it's right here, and it's climbing, and it's pointed in this particular direction, right? So we are going to have this blue aircraft will sort of have a projection to the ground, and let's say that is at this point. So let's say that is at this point, right? And we can have this sort of projected version of the blue aircraft over here. Similarly, we can have an intruder aircraft. So let's have that say at an higher altitude, and it's descending, and it is probably, let's say that it is coming from this sort of an angle and descending. So I'm just drawing these as an example. Let's hope that this example is nice enough. Okay. So then you're going to have as a shadow something like this, right, of this particular aircraft. Now let's say that they collide, right? So what are we going to see when they collide? So this aircraft will have a trajectory that looks like this. And remember, this is slowly climbing higher and higher. And this aircraft is again going to have a trajectory that is going to descend and look like this. And then at some point, their trajectories intersect. And in fact, where they intersect is at the exact same time, right? So for collision to happen, two things should happen, right? So if you imagine the point of time when both of the aircrafts end up at this particular point when there is a collision, right? So let's say that both of the aircrafts are now over here. Then what is going to happen? Firstly, if we look at the ground sort of projected picture, or the picture of the shadows, they'll also have collided, right? So we're going to see that the shadows of the two aircrafts are also going to end up intersecting at this point, right?
Mhm.
So one of the things that should happen is in the shadow picture, or let's say the 2D picture,
Hmm.
we have a collision, right? And the other thing is, this is actually not enough, or this might happen even when there is no collision, right? Because it might be that they're just flying over each other, for example. So to prevent, or so that that situation doesn't happen, the other thing is, whenever they collide, or let's say when the shadows collide, they must have same altitude, right? So these two things characterizes whenever a collision will happen. If a collision happens, then of course the shadows have to collide, and they will have to have the same altitude when they are colliding, right? And similarly, if the shadows collide, and when the shadows do collide, the aircrafts are at the same altitude, then we know that a collision has happened, right? Because the fact that the shadows are colliding, so let's say that you have two colliding shadows like this over here, means that the two aircrafts are somewhere on this line, and the fact that they have the same altitude means they're at this exact same point in this line, right? So there has been a collision. So these two conditions, the conjunction of these two conditions, completely characterize the collision, right? So collision has happened if and only if both 1 and 2 is true. So now number one is actually given by just the 2D picture. So this picture that there is in the GICAT's paper, or that is usually drawn, this is the shadow picture. This is sort of a top-down view. This is looking just at the shadows, right? So this picture is saying that, okay, just look at the shadows and see if things are colliding. So we just have one aircraft going like this and another aircraft coming like this. We are forgetting about the vertical information, and we're just looking at, okay, these are the two positions and relative velocities of the aircraft. And then from that, we can sort of decide, this person will have this trajectory, this aircraft will have this trajectory, and we can check that, okay, actually there is a collision at this point, right? So the first 5 completely describes this shadow picture, the 2D picture. First 5 inputs, right? Because what you need to decide this is just that you need to know the relative position between the aircrafts and the velocities of the aircraft, right? So the relative position is given by the distance and the angle, right? So rho and theta give us the relative position of the aircrafts. Then we know the two speeds of the aircraft. So we have this velocity, this speed and this speed, both of these things we know. And we also know that the angle in which this particular aircraft is traveling, right? So that means we know the relative position from rho and theta. We know our velocity, which is just this particular direction towards, upwards, because we have just oriented the picture so that we are always traveling upwards or towards the top of the page. And we know the relative velocity or the velocity of this aircraft because we know that this is its speed and that the speed is oriented in this sort of a direction. So the first 5 gives us a complete picture of what happens to the shadows. So from the first 5, we should be able to predict whether the shadows are colliding or not. So is this okay?
Yeah.
Yeah. So from the first 5, we can predict if shadows will collide. And we can also predict when they will collide, right?
Mm.
Now, the 6th input, what it says is that it just says that, okay, these aircraft, I don't know, how they're traveling in the 2D plane. The 6th input, it doesn't really know what their actual trajectories is. The actual trajectories might be something very complicated, or, they might be something like this.
What is the 6th input? I mean, I forgot. Yeah.
Yeah, the 6th input is the time until which they are at the same altitude.
Oh, okay.
So this 6th input doesn't take into account the actual trajectories, but all that it says is that, okay, after time tau, your aircraft number 1 is going to be at this altitude. Aircraft number 2 is also going to be at the same altitude. They might be at different positions in the 2D plane, right? But they are going to be at the same altitude. So after time tau, the 6th input tells us that they are going to be at the same altitude, right? So from the first 5 inputs, we know that the shadows will collide after some time. Let's call it this t, right? And the 6th input tells us that they'll be at the same altitude at the time tau, right? So we will have a collision if and only if the shadows collide exactly when the 2 aircrafts are at the same altitude, right? So this is from this 1 and 2, right? The shadows should collide and the aircraft should have the same altitude. So we will have a collision if and only if the shadows are colliding and at the exact same moment the 2 aircrafts at the same altitude. So that means we'll have a collision if and only if tau is equal to t, right? So in this way, from the first 6 inputs, we should be able to tell exactly how they're colliding, or sorry, we should be able to predict exactly whether or not they're colliding. So the inputs are complete. With the inputs, you can sort of characterize the situation as to precisely when they will collide and when they won't collide. It might be some really complicated function, and which is why we're trying to train a DNN to achieve it, or why there is this complicated lookup table. But we should be able to at least predict it. The information is there in the inputs. So is this okay?
Yeah, can you go back to the slide with all the inputs?
Yeah. Right. So the first 5 is for the 2D pictures. Sorry.
Yeah, so time till aircrafts are at the same altitude should be equal to what?
Equal to whatever you predict to be the time after which the shadows will collide.
So you'll have to compute that from the first 5.
Yeah, and then equate it with tau.
Equate it with that.
Yeah. So I mean, of course, it's probably not exactly so how the DNN is doing it, right?
Yeah.
But
Yeah,
if we had to sort of do it by some sort of simulation or something,
could be, but yeah, I mean, functionally, that's how it will be checked.
Yeah. And so this description, at least it tells us that we should be able to do this. It's not like there is not enough information that is in the inputs, right? The inputs give us a complete enough picture to be able to tell whether they'll collide.
Okay, go ahead. Yeah.
And of course, the DNN is actually doing something more than just telling whether they're colliding. It's also producing some advisory, which is adds another layer of complication. Okay, so right, so now, yeah. So now we have these 6 inputs, right? The first 5 basically give us the 2D picture. The 6th one gives us time till loss of vertical separation. The 7th input is just whatever the previous output is. The 7th input just encodes what the network saw as the previous output, right? So if the previous output was, let's say that you have a situation like this, right, where with the 2 aircrafts are approaching, and then in the first time instance, the DNN basically ACAS asks you to turn towards the left. Let's say ask for a turn to the left, right? So in the next instance, it's also going to get this turn towards left as an input from the previous situation. So it can, in some sense, see what the previous input is and base its decision on that, the ACAS system. Okay. So in that sense, there is a like feedback loop sort of a situation involved. But again, whether or not we want to take that into account when we are trying to formulate and verify properties is a different question. Right. So the 7th input is whatever the previous decision was made, right? So the decision in the previous time step. So for example, if you know this person is coming from the left and you turn, you shouldn't just keep turning just because this person is coming from the left, right? At some point you have to decide that, okay, now I turned in the last instant, now I have turned enough, now I can continue to fly straight. So that sort of a decision making can be done by taking into account what your previous sort of advisory was, right? So in that sense, the output is basically getting fed back into the network via this this A pref sort of an input. So these are the 7 inputs to the system. So is that all okay? Are the inputs clear?
Yeah.
Okay.
Yeah.
Sure. So now, right. So now let's talk about the outputs. So the outputs are again going to be advisories that ask you how you want to turn. That basically will command a particular kind of turn out of the aircraft. And again, the idea is that the network isn't actually controlling, say, the actual wings and flaps of the aircraft and so on. But there is some other control system that is handling that. The network is just going to tell you that, okay, I want a turn in this direction of this particular, with this particular sharpness and so on. So there are 5 possible sort of outputs the network can produce. The first is, of course, clear of conflict, which just means that keep flying straight. Nothing is wrong, right? The second is a weak left turn. So basically the other things, these are turns, and the turn can be towards the left or towards the right. And it also can be weak or strong. So you have just 4 possible output commands based on these 4 combinations of turns that you can have, right? So left and right is of course clear. Weak turn means it should turn at 1.5 degrees per second, and the strong turn should be something at 3 degrees per second. Okay. So this is the idea of what the turns are. And the way that the ACAS system is expected to produce this output is that it should produce 5 scores, right? So for each one of the corresponding output, it will produce 5 scores. So you'll have a score for the clear of conflict output. You have a score for, commanding a weak turn to the left, a score for a weak turn to the right, a score for a strong turn to the left, and a score for a strong turn to the right. And then the advisory with the lowest score is picked. So this is actually very different from what we usually do with DNNs, and which I think is also more intuitive. It's not entirely clear why they chose to do it this way, but it might be due to some sort of compatibility reasons with the TCAS system. I'm not aware of it. But the way they do it is usually is sort of flipped from the usual sense, right? So usually you would take your outputs on the DNN and then do whatever the highest output asks you to do, right? But in this case, we're doing the opposite. We are just going to follow the advisory, which has the lowest score. Of course, it really doesn't change anything or matter much in a technical or sense, because you can always just train a DNN with the fact that the output with the lowest score is picked in mind, right? So you can train a DNN so that in the training set, you will have the correct labeling should have the lowest output, right? So while training, you somehow penalize outputs which are wrong being high, and you reward if the correct output is low, right? So you can always do that. You can always just flip the loss function when you're basically doing the training, right? So the fact that you're using the lowest score to pick the output is not something that is hard from or any different from the usual situation from a technical point of view, but it is intuitively something that we have to keep in mind, because it's not usual. At least I have not found too many situations where people do this. But yeah, what they do is they'll pick the advisory with the lowest score, and that is considered as or that is basically the alarm that the rest of the system or the pilot or whatever will get to see. Okay. So this is clear. Okay, so all of these inputs and outputs.
But you haven't. Did you describe how the score is computed?
Yeah, so the score is actually there is no sort of like, in the sense that there is no very particular standard for computing this score. The idea is
what
that.
Does it mean then? Advise if the lower score is picked. It gives 5 outputs.
Right. So in the sense that, for example, when we do the image recognition, the 5 outputs correspond to probabilities of picking of the network thinking that this particular image is that particular character, right? It's a similar sort of situation here. So, for example, each score basically represents that the amount of confidence that the system has that this is the correct decision to take in this particular situation. So,
I see. So that is like a number that is printed. I mean, that is output. Okay.
Yeah.
So this is not this.
This particular score number doesn't have any significance from the actual physical picture point of view. Yeah. Okay. It's just some internal number that is used to
Yes. So with each of these 5, that number is what is decided to pick.
Yeah.
If number 2 is picked, then it will turn left by 1.5 degrees.
Right.
Okay.
And when number 2 will be picked, it'll basically be in the situation where number 2's output is the lowest. So only the ordering among these things matters. The real actual value of this actually doesn't matter. And in fact, these sort of actual reward values, they are, the people usually tweak them via various techniques when doing the training. So if you remember the way the original ACASS system, the non-DNN system, the lookup table system, that was actually trained via some like by modeling an MDP and then doing some sort of dynamic programming, right? So this was modeled as an MDP, and then dynamic programming was done on that. So in this MDP modeling, there would have been some reward function. And then that reward function is what would basically, in some sense, influence what these sort of scores will be, but not in a very direct way in which we can interpret what the actual score values are. Or I don't think that it actually even matters that much in that sense, right? So if you for example say that the reward for having a collision is -1 and not having a collision is +1, then you might get some sort of scores, and you're going to compare and decide based on that. You can also say the reward from not like having a collision is -1000 and the reward for not having it is +1000. You would again get some sort of scores, but more like it's likely that these scores will basically be this similar to the scores you were seeing previously, but just multiplied by 1000, right? So in that sense, the exact values doesn't really matter. It depends on the choice of the reward function here. And again, once the training is complete, then the reward function doesn't come into the picture when we're actually deploying it or verifying properties about it. So at least that is what like one perspective it is, I guess.
So, I have one question.
Yeah.
Actually, in most of the deep learning networks,
can you identify your name?
I'm Deborshi.
Yeah.
Okay.
So in normal CNN, the output is generally the probability distribution over the classes. So is something similar output here? Or
so that is what I'm trying to say, that is not really the case. It's not really the case. So I'll tell you what. So basically what we do in normal neural networks is, or in other scenarios, is that we try to get the output and then somehow convert. So let's say that you've got 3 classes, right? So you'll get some outputs for each one of them, and then we somehow interpret that as a probability distribution, right?
Yes.
So for example, with if you were in the assignment in the MNIST sort of DNNs that you trained, the outputs are coming from ReLU nodes, right? So then we were passing them through softmax functions, and then we were doing a normalization, right?
Yes.
So these 2 steps is converting whatever output we're seeing here to a probability distribution here, right?
I think softmax will normalize the input, right? Whatever input we give, if we pass it through the softmax function.
Softmax only looks at one particular input, right? So softmax is just this, right? Softmax is just 1 by 1 plus e to the power x, right?
I think e to the power x by summation of e to the power x, right? That way also.
Yeah. So that is I think that is not the softmax function. That is basically softmax, and then the second, when you divide by the summation is the normalization step. So I might
okay. I mean, same thing.
Yeah, it's the same thing, but like what I'm trying to say is that's some extra step that we do after the network, right?
Yes.
You can sort of say that, okay, I have a softmax layer here, or a softmax plus normalization layer here. Sure, right?
Yes.
But if I ask you, okay, what does the raw output of the ReLU mean? Then we can say that, yeah, you can do these calculations and interpret that as a probability distribution, but the raw values don't really mean anything in that sense, right? Like in a very absolute sense, they don't mean anything, right?
Right.
Yeah, so similar sort of situation is happening here. Here also, you can definitely just somehow interpret this as a softmax distribution, or sorry, as a probability distribution, right? So for example, one thing that you could do very naively is take the negative of this scores and then pass it through softmax, right? Then what you would get at the end is a probability distribution. And if you had done this while training the network, then the network would have learned that, okay, what you're doing is a probability distribution, and it would have optimized itself accordingly, right?
Yes.
So you can always interpret that as a probability distribution, that is fine. But the raw scores that you're getting, you're not going to be able to interpret.
Yeah, understand. I mean, I was just asking whether the softmaxed output is given.
No, it's not.
Is
it's
generated
not
or
used.
not?
Yeah, it's not used. It's not used.
Yeah.
The softmax is actually not used anywhere in this thing. So basically, so reason why you would want to take like a probability distribution, from at least what I understand, is once you have a probability distribution, you can compare that distribution with a target distribution, right?
Yes.
And there you can do something like cross entropy or something like that, right?
Yes.
So what they're doing is actually not that, like in a sense, they're not training it by generating a distribution and using cross entropy at all. So what they're doing during the training is much more direct, in the sense that they're training directly that the minimum should be what the lookup table says. So remember that the lookup table is already generated via some optimization or some dynamic programming algorithm, right?
Sure.
And what they're doing during the training is just that, okay, we are going to give, we're going to see the expected probability of the lowest output being the lookup table. Okay. And the way they're computing this expectation is just by doing a bunch of samples and seeing, okay, how many times is the lowest one actually the one that is there in the lookup table.
Okay.
Right? So yeah, they're not using this sort of this thing. And I'm not sure, like, if there is any motivation why they're not using it, or which one will be better or worse from, a training perspective. Might be that this using cross entropy, like I think that cross entropy would probably converge faster. But in any case, this particular work, they didn't use that too much. And of course, when they were generating the lookup table, it wasn't even like, it wasn't even a learning algorithm. It was just some dynamic programming algorithm, right? So does that answer your question?
Yes, thank you very much. Yes,
Yeah.
thank you.
Okay, so this is basically what's going on. And yeah, so this is something that we'll have to keep in mind when we formulate our properties, because our properties would basically also involve comparisons between the outputs of the network, right? Okay. So if the outputs are clear, then I'll just go into actually what the networks are. Okay, sure. So the way that they trained this, okay, this is not there in the original paper that did the DNN compression, but after that, people have sort of figured out that it's easier to use some discretization before doing the DNN compression. And I'll say what I mean by that. And that is the standard that people have converged as, in terms of at least, the standard DNN compressed version of the ACASS involves these things, right? So, okay, the way that they're using a DNN in this case is that they're not going to pass all 7 inputs into one DNN, right? So they're not going to take all 7 inputs and then pass it to a DNN. So this could have been the at least the direct or naive way of doing it, and get 5 outputs, right? Instead, what they're going to do is they're going to take the last 2 and then discretize them, which means that they're going to sort of split it in your input space into several regions based on what the values of the last 2, or what the range, or what range the values of the last 2 inputs fall into, right? So they're going to discretize based on the last 2 inputs. So the last 2 inputs, if you remember, are tau, which means time to collision, and aprev, which is the previous action that was done, right? And the way that they discretize is that aprev is already a discrete thing, right? Because aprev, remember, there is only 5 actions that could have been performed: turn left or right, turn strongly or weakly, and or don't turn at all. So those combinations of the first 4 and then the 5th one. So there are only 5 sort of advisories. So it is already discrete in some sense. For tau, they took 9 possible values, right? So they chose these values based on sort of the distribution of tau that you usually see in real life situations for which this is aimed at. So one of the values is 0, which basically means that both of the aircraft are already at the same altitude and they'll remain at the same altitude. Then you have 1, so they are going to come into the same altitude in 1 second. 5, 10, 20, 40, 60, 80, and 100, right? So these are the 9 values of tau that they chose. Then what they did is that based on, so you're getting some 7 inputs, right? So you're getting some 7 inputs. Now, based on these last 2 inputs, you remember you're getting a value of tau here. So you'll see which of these 9 values you're closest to, right? So let's say that you're closest to tau 3, right? And then you have some particular value of aprev. So based on this and this, you're going to choose one of 45 different DNNs that they trained, and then feed the rest of the 5 inputs to that DNN. So they basically have this set of 45 DNNs for each combination of tau and aprev. And based on the value of tau and aprev, they'll choose one of these 45 DNNs. So they'll choose, say, DNN 3, and if aprev was, say, COC, or clear of conflict, they'll choose DNN 3 clear of conflict, and they'll pass the rest of the 5, the 2D picture inputs, to this DNN, and then this DNN will again produce 5 outputs, and then the rest of it is the same. Then this produces 5 outputs, they pick the smallest, right? So this is basically the idea behind having these, or the way that they use DNNs here is, right? So instead of having one huge DNN, they'll have 45 different ones, one each for the combination of tau's discrete values and apref values. And each DNN will only see the first 5 inputs. So in some sense, each DNN only gets this 2D picture, the shadow picture that I was talking about, right? And then each DNN is separately trained on, scenarios or on the parts of the lookup table where tau has this specific value and apref also has this specific value. So each one of these DNN essentially specializes in the particular set of scenarios where, say, tau is 0 or tau is 10, and learns how to give turning instructions for only those scenarios. Then, before you actually query the DNN, you make sure that you're using the value of tau and apref that you're seeing to choose the right DNN to query. So this is sort of the discretization step that happens, right? So is this discretization concept here clear to everyone? So sort of, flowchart sort of a diagram would be something like this. You have your 5 2D inputs. So your inputs are 5 2D inputs, and then you have tau and apref. This tau and apref is fed into a switch, which then will basically take the other 2D inputs and send them to one of 45 different DNNs, right? And then again, you choose the output from that particular DNN, which corresponds to the correct tau and apref value. And that is the output that is finally given by the ACASSep system, right? So is this sort of picture clear? Like
Yeah.
Yeah. Okay. So yes, essentially each DNN only needs to worry about some slice of the entire input space. The good thing about this is that it reduces the input dimensionality, which might or might not be a factor. It's not a factor during training with modern techniques, but it might be a factor during verification. But definitely it will basically mean that each one of these DNNs is in some sense at least learning a simpler problem, right? Like it's definitely learning the problem for the special case of tau equals 20 is definitely simpler than this general case where tau can be anything. So that is the basic idea of the way that discretization happens. So if this is clear, then I'll just talk about what the layer structure of the DNNs are. So of course, each network is 5 inputs, right? 5 inputs corresponding to the 2D picture. Remember, tau and apref are not being actually fed into the DNN, they're just being fed into the switch. There's sort of an implicit input to the DNN if you think of it that way, as they are being used to decide which DNN to choose. But yeah, they're not inputs to the DNN itself. Then you have 5 outputs, as always, with the turns, strong and weak turns, and no turn. Okay, so then each DNN, other than that, has got 6 hidden layers with 50 ReLUs each. And the important thing is that the output layer actually has got no activation, right? So the way it looks like is this. You have 5 inputs. So this is a 5-dimensional input vectors. And then that gets fed into some ReLU layer. So you have got ReLU activations all over here. And this is again 50. And then, you'll have another ReLU layer, which will again have 50. And so on, 6 times. So you'll have 6 many of these. And then the final ReLU layer, which is again 50, is going to feed into 5 nodes, which have no activation. So remember that these actually have, so when I say no activation, I mean that the activation function is just identity, right? Sort of similar to how in the input side, we don't actually do an activation function, right? So, and then you just get the output. So this is basically what the structure looks like. So any questions so far at all? No?
So I just have a question. Like,
Yeah.
the structure is, if the input is a 5-dimensional this input layer, and what do you mean with 50 ReLU layers? 50 like nodes.
Yeah. There are 50 nodes in the ReLU layer. So essentially, like your first layer, for example, is going to look like this. You're going to have exactly 5 inputs. So there'll be rho, theta, and then chi, and then the two your own velocity, intruder velocity, right? And then you're going to have 50 neurons over here. And you're going to, everything is connected to everything via some weights, right? And then each one of these neurons is doing ReLU. You're getting an output and so on. Again, in the next layer, again, you'll have going to have 50, everything is connected to everything in between. Does that answer your question?
Yeah.
Okay. So any other question? So just to point out, like in the assignment, at least in the first few questions, the architecture that we asked you to do, or even up until this point in the examples that we've been talking, there is usually some activation function, something like ReLU or something at the last layer, right? This is an exception in the sense that the last layer actually doesn't have any activation function. The last layer is just a linear layer, and then you get the output. Also notice that this network is a ReLU network, which if we go back to some of the previous, like in one of those previous lectures, we're talking that the ReLU network is basically just a piecewise linear function, right? So that is something that we can already utilize here potentially when we're trying to do the verification. And it's also fully connected. So there is no, convolutional layer. There is no recurrent layer. There's nothing of that sort complicating the situation here, right?
So Diganta, it's 7:30 now. So I think you have to plan on how long you want to.
So
what is it that you want to cover today, and what the plan, if you want.
So I'm actually
to look at things and experiment, you might have to say something.
Yeah. So it's 10 minutes more. Is that okay for
with 10
everyone?
minutes should be fine. Yeah.
Okay, sure. So this is all the slides I had. This slide actually tells you where to. Okay, so before that, I should probably talk a little bit about the properties. So in terms of the properties, they're actually the properties that is sort of emerged as standard is given by in the ReLUplex paper, right? And this is the property that you will get in, say, all of the neural network verification benchmarks and so on. So of course, you can actually experiment with various different kinds of properties, right? One of the parts of this entire field that is being explored right now is even like what kind of properties make sense, right? So for example, you can consider a really complicated property which takes into the entire feedback loop into the consideration, right? So you have the ACASSep8 feeding some sort of a aircraft controller, which is again feeding back into some sort of a actual simulation with 2 aircrafts, and then that is again feeding into the ACASSep8. This entire closed loop you can consider, and you can consider whether several iterations later a collision will happen or not. Or you can consider the simple local properties, right? You can consider various like robustness properties, various invariance properties. So you can sort of try and devise many different properties. But the ones that I'll just briefly mention here is some standard properties which have emerged, like some properties which a lot of people have looked at and tried to develop or try their own sort of verification methods on, which are again given in the ReLUplex paper. And these properties are basically based on these 3 points, right? So one is that, this network shouldn't produce any unnecessary turns, right? So under some situations where things are obviously safe, the answer should always be clear of conflict. Then, it should also make sure that there is some consistency, right? In the sense that if your aircraft is right here, if the enemy aircraft is right here, then you shouldn't actually ask it to turn to the left, right? You should always make sure that, sorry, ask it to turn to the right. You should always make sure that in this situation, you're asking to turn to the left. And finally, this last one is actually based on the fact that most aircraft can't climb and turn very well. So if you are in a situation where the two aircrafts have high tau, that means that like they probably have a really good vertical separation. So they're probably in a situation where one is low and the other is high or something like that. And there is a lot of vertical separation between them, and this vertical separation is not reducing very fast. So you'll probably not collide immediately. So it makes sense that the turn that you would want is not going to be very strong, right? So these sort of properties were talked about in the paper, and they have given a list of 10 properties, and these 10 properties have become sort of standard. One of them I have over here. So for example, if the intruder is far away, the intruder is far, and the intruder is much slower than you, then clear of conflict, the score of the clear of conflict output should be below a certain threshold, which means that clear of conflict output should be, somewhat preferred. It should be, so by the fact that it being below a certain threshold is basically means that it should be close to the minimum, right? So then you can sort of write this property formally as this sort of a pre and a post pair, right? The pre is that, of course, distance is rho. So rho is going to be greater than equal to something. And your own speed is large, so it's greater than 140. And the intruder speed is small, so it's greater than 60. Then the post conditions is that, okay, if these things hold, then clear of conflict should be less than 1500. Again, the precise values is something that we won't really worry about. And so the precise values of the precondition are motivated by actual real life data from how planes fly and what the speeds and distances of planes usually are and so on. Whereas this threshold for the clear of conflict value is based on what sort of values appear in the lookup table, and that is dependent again on the training process and so on, right? So the actual values doesn't matter. They're listed there in the paper, but the properties are of this sort of a kind. So is this clear?
Yeah.
Yeah. Okay. Sure. So the final thing is, I sort of say that like okay, so maybe I'll not go over this, but I'll basically post all of this there into the Moodle page. But you can get these sort of benchmarks from the VNN Comp 2022 benchmarks GitHub. So this is a list of benchmarks for a number of neural network verification sort of like problems. And there they use this particular file format, which is kind of tricky to work with, which is called ONNX. Okay. The issue with ONNX is that this is actually meant to sort of support things other than ReLU-DNNs, things other than fully connected. So it supports things like convoluted neural networks, recurrent neural networks, LSTMs, all of these things it supports completely, right? So which means that it's a very general file format, and it might be somewhat difficult to work with it. So yeah, I'll give maybe another tutorial about how to deal with ONNX. I hope that I would be able to do it today, but I think I don't have time anymore. Okay. In any case, I'll put out some links and I'll send a file demonstrating a few things about ONNX. But yeah, other than that, I think this is it. So any questions?
Yeah, while we, okay, no, if there are no questions, I'll wait. I just wanted to make a comment. Yeah, my comment was, what is it that while we, define the project problem between next, if they want to be, after they download this thing, if we want them to be looking at the train data, running and doing things, what
right. So I'll maybe say something along those. So
I can definitely encourage all of you to start getting acquainted with the entire network and its components, and do some useful experiments, including what Diganta will be suggesting.
So first thing that I will say is that read this particular appendix in the Reluplex papers. In the Reluplex paper has a, okay, so maybe just pull it up. Just a second. Yeah. So this Reluplex paper has appendix 6, and this talks about the properties, right? So you have the list of 10 properties here. Just go through these. You'll get some idea about what the properties are. You don't like, we will come to and discuss the rest of the paper in detail in due course. This is a really relevant and interesting paper for us, but in general, you can start looking at this section, the appendix 6 of this, which has all of the properties listed. Then I also would, it would be nice if you would actually go to this link, which I'll post, which is this GitHub link, and download all of the benchmarks, right? So in this particular link, they'll be there on the Moodle. You download all of the benchmarks. The ONNX files, you will probably need like a Python ONNX API to open. You can install that, but it is not very well documented. So you can try looking at the documentation and figuring it out. You can definitely open these DNNs, into TensorFlow from ONNX, that sort of a thing they have described. The other thing that you can actually do is look at the VNN lib files. So these are the files that describe the properties. So ONNX are for networks and VNN libs are for properties. So we have the network and the property. The VNN lib files are actually looking just like SMTlib2 files. In fact, they can be feed them directly into Z3. They are exactly sort of an SMTlib2. They're basically trying to emulate the SMTlib2 standard for neural networks, and so far they are human readable. They have assert statements just like SMTlib2 files, and they look almost identical. Okay, so you can just download them and start looking at them, and you can see that they're actually encoding the properties that are listed in the paper. Okay, so these two things you can do. There is one thing that you can do with the ONNX files, which is that there is this particular website called just a second. Yeah, this netron.app, this particular website, and there you can actually visualize the ONNX file as a graph. So a graph, which shows the flow of operations that you need to do to get the result of the DNN. So for example, here it's, I don't know if it's visible, so I'll maybe make it a little larger. So here basically it's input and then some subtract and then multiply and add for the weights and biases, and then ReLU and then so on. So it gives you this sort of a graph, right? And you can look at any of these nodes. You can look at what inputs and outputs they have and so on. So this will give you an intuition as to how these files are sort of structured, and then it'll help you. So these are the few things that you can do. So I'll maybe make a point. So number one is read Reluplex. So I'll upload the paper as well. Appendix 6. Number 2 is download the VNN files. And read them. Right? See that you can actually also think about parsing them. So think about how you can write a Python program to read them in and parse them. So because these may be steps that we need to do, like this is ultimately front end for us, but still we'll have to do that. So think about parsing them. I'll post a link to some parser libraries that might be useful. So things like S expression parsers might be useful. And then number 3 is download the ONNX files and then open them via netron.app. Right? And of course, you can always explore all of the other benchmarks in the 2022 VNN comp category as well. So, those might also be interesting. But yeah, these three things I think you should do and start getting a little bit familiar, at least a little bit, dipping your toes into this, and then we can do more experiments as and when, right? And you can also try using the Python ONN API. You can try using this to open these ONNX apps. Sorry, don't files. And then reading them, trying to see if you can, get the weights and bias values out of them. Or if not, can you, open them inside of TensorFlow? So all of these things you can try, right? Or the PyTorch or TensorFlow, whichever one you prefer. So I think we talked about PyTorch in the tutorial, so PyTorch. But yeah, there is this ONNX API. So the ONNX API, you should install this. So this is just do pip install. Sure. So I'll put a link of all of these. I'll put these instructions up as well. But yeah, try all of these things. Okay. So any questions? By the way, does anybody have any experience writing, say, something like an S expression parser?
I guess that's a no.
Yeah, sure. I mean, they're not very complicated things, and we can help you guys out as well.
Be best as a comment. Okay, not me. Yeah, I think we should plan the content. That's what we have been talking about. Some small assignments.
Yeah, definitely.
Where they will be, required to.
Yeah, so maybe what I can do is I wanted to cover the parsing of the opening ONNX files today, but I couldn't. So I'll write up a document on that, and at the end I'll have some exercises where you can follow along.
Will it be useful to? I guess it won't be useful to go into the structure or look into a couple of those 45 DNNs. Does it even make sense?
Yeah. So the
or just run it on some.
Yeah, definitely. I think it's a good idea to run it and simulate it on some.
Yeah, that's what I was thinking that they should do.
Yeah.
Give them some inputs and they can run it.
But the issue, right? So even before that, we'll have to actually be able to open up this .onx files and load them.
That's right. So that is 2, 3, and 4. What you have said is should have the move towards that. And after that, maybe we could give some exercises.
Yeah. So right. So I had actually hoped that I'll be able to cover how to open and work with this .onx files inside Python, but I'll write that up and send that to Moodle, and then so do you think it will be okay if I write that up and send it to Moodle, and then you can take a look at it offline? If you guys have questions, then you can just always contact.
Right. Yeah. So there's a question, if Z3 assignment will be coming soon. Yes, I'm working on it, and I will get it, we'll put it out before the week is over. Yeah. Okay. Yes. So that should be, I think then we could end on that note.
Yeah, sure.
There's some questions. Any more questions? Okay. Thank you. Have a nice dinner and